Hi, this is Math 1650, and this video is over section 10.2. And we are looking at regression now. We have looked at correlation before. Now we're going to look at regression. Let's look at this graph. We have a graph of shoe print on your X and height on your Y. So as you have a higher shoe print, does that mean you're a taller person? Looking at this graph and examining for correlation, there does seem to be correlation. Okay. So if we had the data, we would conduct a correlation test. And pretty sure we do have the data, so let me pull that up. So I'll go back to this, I'll delete this data. Let's go, I think it's in the 14. Maybe not. Shoe print, right, okay, yep. So we'd run a correlation regression. We're looking for shoe print, and then we're looking for height. Yeah, shoe print. Evaluate. And we get the fact that we have a p-value of 0 and a correlation coefficient of 0.812. So R is 0.812, which is going to be greater than 0.312. And our p-value is, or p-value is equal to 0, which is less than 0.05. And we look at the plot, and we see it's pretty much the same plot we have on the paper. All right, so we do have a correlation there. Now we want to determine the regression line. It's given up here actually. 80.9 plus 3.22x. Now, the way we get that on StatDisk, and you actually already have it on StatDisk, go back to the results. We have a y-intercept. That's our 80.9. Then we have a slope. That's our 3.22. Rounded to a second decimal point. Okay, and then we can use this in terms of height and shoe print. We can say the height equals 3.22 times the shoe print plus 80.9. And so we can use this to actually predict a value if we measure somebody's shoe print to see what the height would be. Now, if there isn't correlation, the only thing we could do is look at the average height of a person. So the idea is this will give us a better way of calculating a more accurate estimate than just the average height of people. So if, let's say we are looking for somebody who has a shoe print of 25 centimeters, their height then is going to be equal to 3.22 times 25 plus 80.9. I get 161.4 centimeters. Or, let me get the height is in. Doesn't say. I don't think that's centimeters. It could. No, it's not. Maybe it is. We'll just not worry about units right now. I have to look and see what the height, the units for height is. Okay. So, assumptions with regressions. First, we're only looking at linear regression. So only concentrating on linear regression. Second is that our x value is a normal distribution random variable with some variance. Then third is y has a mean that lies on the regression line. Right, so let's look more at the regression equation. Y equals mx plus b is a general line for equation that you may see in the algebra class, where x is your independent variable, y is your dependent variable, b is your y-intercept, and most importantly in statistics, m is your slope, or your rate of change. And so we write ours as y equals b1x plus b sub 0, but these have the same meaning. B sub 0 is your y-intercept. Though it has the same meaning, it's not always useful. B sub 1 is your rate of change, or your slope. And those specific equations we use to find these, or status is going to use to find these. But you already saw, if we really do want to find these values, we plug that into StatDisk, and it gives us the equation which gives us these values. Again, if there is correlation, then we can use the regression line, regression equation to predict. And then if there isn't correlation, we use the y mean or y average to predict. Right, so let's do some examples here to really run these. So we're going to be putting a lot of this data into StatDisk. Let's go back and clear this data here. So we're going to do different types of the different blood pressures here. So name these. So diastolic and systolic. And we add these in the columns. So 138, 130, 135, 140, 120, 125, 120, 130, 144, 143, 140, 130, 150. And we have to have the exact same number, and they have to line up. So if I missed one, then I may have to go back and adjust everything. So key is not to miss one. Make sure everything is lined up. And I may have missed one. So let me just go through these again. 82, 138, 91, 130, 100, 135, 100, 140, 80, 120, 90, 125, 80, 120 again, 80, 130 twice. That's the one I missed. Right, so 80, 130 twice. And double check these. 144, 98, 143, 105, 140, 85, 130, 70, 150, 100. It's really important that you have exactly the same amount because it's going to throw up an error if you don't. And it's really important that you have them lined up together, otherwise your numbers will be completely off. Alright, so now we'll do a correlation and regression. And so we'll do stoic, systostoric on the X, diastolic on the right, or not on the right, on the Y. We'll look at the plot first. So it looks like an upwards increase, maybe not drastic. There's not a lot of sample size, so just because there's a slope doesn't necessarily mean there's going to be a correlation. So let's look. We have a R value of 0.658. And we're going to compare this. Since it's positive, we'll compare it to the positive side. Critical value of 0.532. And we have a p-value of 0.01. And we're going to compare it to a p-value of, or not p-value, significant level of 0.05. Okay, so p is less than the alpha. And the critical value is less than the correlation coefficient. So the correlation coefficient is greater than. So we do have correlation. Okay. Now that 0.658 may be moderate. And that could be because we only have, what was it, 14 data points. But that still means we have correlation for the data we did get. And now we want to look at the regression. So for the regression, we can write this as the diastolic equals the slope, which is 0.769, times the systolic minus 14.38. And so if we read a 122 for the systolic, then we do 0.769 times 122 minus 14.38. We get 79.44. Okay, and that's our prediction. All right, so we have correlation. We can use that regression equation and give us a value we can actually rely on. Okay. Let's get into some actual hypothesis tests. This one we are going to look at lemons, vehicles that is, but lemons. These lemons are vehicles that are kind of new and they come off and they just have problems that they're not good vehicles. And we're going to compare these to crash fatality rates per 100,000 population. So these numbers are in the unit, the fatality rates are in units of 100,000. So if it's 15.9, it's not 15.9 average people, it's 15.9 100,000 people. All right, and so we're going to see if there's correlation and basically do a hypothesis test on that, and then see if the regression equation, what it is and does it matter. All right, so let's get these into StatDisk. So go back to this, we can clear this data. Change these names. So lemons. And crash fatalities. Don't know if there's a limit on how many letters I can put in the title. And so we'll do 230, 266, 359, 483, 533, 15.9, 15.6, 15.5, 15.2, 14.9. And then before we do the analysis, let's look at the graph. So lemons, and save. Okay. Maybe that's too long. Let me see if I can do that. Take this out. No, it's just not doing it. Okay. Anyways, so we'll look at the plot, and it looks like there's a downwards slope to it. So the higher the tonnage on this lemon, the lower number of crash fatalities. All right, so let's go back and look at the hypothesis test. So again, you will look at hypothesis where there's no correlation, or R is 0 as your null, and then the alternate is correlation and R does not equal 0. So we are looking at a graph that's a two-tailed. So let's get these values now. So R is negative 0.9696. Critical R is 0.878. Test statistic, we'll have to calculate that. P-value is 0.0063. That's these values. Let's calculate this test statistic. We had it before in section 10.1. T equals R over the square root of 1 minus R squared over n minus 2. So I'll write this out. T equaling R over the square root of 1 minus R squared over n minus 2. Let me just double check that. Yes, okay. All right, so it's going to be negative 0.9696 over square root of 1 minus 0.9696 squared. I'm not putting the negative in there because we're squaring it anyways. We have 5, so 5 data values, right? Yeah, so we'll have 5 minus 3 on the bottom. So let me get this. I get test statistic of 5.6, negative 5.6. All right, so based on this, our R coefficient, which is negative, and so we're comparing it to a negative critical R, it's still the absolute value of it's still greater than the 0.87. Okay, so we will have correlation. And we reject the null. I'll write this in here. Okay. So somewhere our value is falling to the negative side, somewhere in that test region. Okay. We don't actually find these critical t's in a sense, but because we're using the R coefficient, but it still has the same idea. I know it's on the negative side because the value is negative. All right, so we can say there is evidence that there is a correlation between the weight of lemons and crash fatality. All right, so do the results suggest that the import lemons, or I should say the weight of the import lemons, cause car fatalities? Okay. The results suggest that the higher the weight, the lower crash fatalities. Now let's look at the regression equation. The crash rate is going to be equal to negative 0.0028 times the weight of the lemons plus 16.47. And yes, it's valid because we have correlation. Okay. Let's look at another scenario. We have advertising, cost of advertising in thousands of dollars, and the number of products sold. We want to see if there's a correlation between the cost of advertising and the number of products sold, and then we'll estimate what the advertising or based on an advertising cost of $7,000, how many products should we expect? Right, number of products sold in this case is in thousands, and so is the cost of advertising. But, since they're on the same units, we're just using the whole numbers to run the data. Right, so let's add in the data to this. So we'll have to clear this. Let's see if I can change the titles. Again, it didn't work last time, but hopefully it will work this time. So let me clear that out one more time, maybe that will help. Right, so we'll put cost and then products. And we'll do 9, 2, 3, 4, 2, 5, 9, and 10. And A5, 52, 55, 68, 67, A6, A3, and 73. Alright, so let's graph this real quick first. So cost is going to go with products. And we're going to plot. And it looks like we have a upwards trend with this. Again, we only have 8 data values, so hopefully this is a correlation. It looks like it's going to be. All right, so let's go back to this. So our hypothesis again, null is R equals 0 or no correlation. Alternate is R does not equal 0 or there is correlation. Okay, let's get our values here. Our value is 0.708. Our critical value is 0.707. Very close. P-value is 0.0495. You could even round that up to 0.05, which is good. So they asked for test statistics, so we'll find just that. All right, so do we have correlation? Well, this one is very, very close. And the fact that our critical is just slightly less, we can say we reject the null, that there is correlation. But it's barely any correlation. So there is evidence of correlation between cost of advertising and number of products sold. And it's possible that the reason it's so close to almost not having correlation is because maybe there's a lot of factors that come into this, and so it's kind of muted down some. Right, we can look at the regression equation. So products equals 2.788 times the cost plus 55.788. And so is this equation valid? We would say yes. There is correlation. And so if we want to know what the value or what we can expect for the number of products based on $7,000 in advertising. It's going to be 2.788 times the 7,000 in advertising. We'll only put in 7 because of all our data used. Just the number in front didn't include the thousands. Plus 55.788. We get 75.304, the cost of advertising. Or, I'm sorry, that was the cost of advertising for the number of products. Okay. Let's do another one. That's one we're going to use the data set that we have. It's going to deal with IQ and brain size. So is it true that somebody who has a high IQ has a bigger brain? That's what we're looking at. Our hypothesis, again though, is going to be the same. If r equals 0, we have no correlation. And if r is greater than 0, or does not equal 0, I should say, there is correlation. All right, so let's pull up this data set. So 13th, IQ and brain size. And then we're going to pull up the correlation regression. And we're going to do volume is going to be our X. IQ is going to be our Y. So volume causing IQ. That's what we're looking at. Right, so the plot wise doesn't really seem to be all that much of a correlation. Okay, so let's see how the actual results come out to be. Our R value is negative 0.063, really low. Our critical value is, we'll look at negative 0.4438, much higher than the correlation coefficient, absolute value wise. P-value is extremely high, 7.7906. So our results are clear. We do not have correlation. Okay. So conclusion-wise, there is no evidence that having a larger brain increases your IQ. Right. So what is the regression equation in this case? Well, we still have the values that are given. The IQ equaling negative 0.0067 times the volume plus 108.55. However, this equation is not valid. Right. So kind of just ignore it. It's not important. So what we do to find the best predicted value for someone with a brain volume of 1,000 centimeters cubed, the only thing we can do from what we have is that we have to ask ourselves, what is the average IQ? Right. So we'll go back to status, go into data, explore data, IQ, and we get a mean of 101. So y mean equals 101. And so in this case, a 101 IQ is what we expect given that brain size or any brain size, since there is no correlation with it. Alright, so I think we got a couple more on here. So let's get these last two done. A researcher is interested in whether there is a correlation between patients' age and their recovery time after a certain type of surgery. The researcher gathers data from 10 randomly selected patients, recording their age and recovery time. So we're only looking at age and recovery time. So the patients is just kind of like the row numbers. It's just what patient is what. Is there a significant correlation between the patient's age and the recovery time? All right, so let's get the data in. Clear this. Try this again with the title. See if I can get it to finally work. Age. If not, oh well. Recovery. Oh, still didn't come up. Okay, 30, 40, 35, 50, 60, 45, 38, 55, 33, 48, and then 8, 10, 9, 12, 14, 11, 10, 13, 8, and 12. Now we're going to look at the data. Let's just do it this way. So age, and recovery time. So looking at a plot, it looks like there's correlation. They're all really close to a line, and it's a pretty high slope. Looking at the results, 0.99 is your R value. We're talking pretty high R value for sure. And so your critical R is very low, 0.632. P-value is 0. Significant level is 0.05. Right, so when your p-value is 0, that usually means your data is going to be, well, I mean, it pretty much definitely will mean your data is going to be correlated. Right, so absolute value of R is greater than R critical, and p-value is less than your alpha. So there is evidence of correlation. And then we can write the regression equation, time, recovery time that is, equals, let's get the values here, 0.207 times your age plus 1.73. And that would be your equation to estimate the recovery time based on somebody's age. All right, one more. Manager at a retail company wants to investigate if there is a correlation between the amount of money spent on advertising and the revenue generated in different months. Very similar to what we were looking at, but instead of products, they're looking at revenues. Uh, and they're looking at over months. Data is collected for 12 months, showing the advertising expenditure in thousands and the revenue also in thousands. Is there a significant correlation between these? So let's put the data in. Okay. Just double checking here. Okay, so let's look at the graph. Definitely looks like there's correlation, pretty steep. So let's look at the results. Pretty high values here. R is 0.988. Our critical is 0.576. P-value is pretty much equal to 0. Alpha is 0.05. I'm just going to write out the regression equation then. So then revenue equals 5.75 times the advertising cost plus 132.78. Right, so R is greater than the critical, p-value is less than the alpha, so there is correlation, making the equation valid. And so now we have a regression equation to predict, based on advertising costs, what the revenue will be. All right, that is the end of not just chapter 10, but the class notes in general. Good luck on the final. Bye.